Alright, this is the second presentation about two-sample inference. What we're going to do in this second presentation is a hypothesis test. Okay, and in this case, sigma 1 and sigma 2 are known. So we're going to do a hypothesis test about the difference of two population means. So that's it there, mu1 minus mu2. Now this follows on from an earlier example where we're looking at, just in case you missed it, we're looking at two golf ball companies, Par and Wrap, and we were interested in seeing if there was a difference in the distance that the golf balls can go at. So can we conclude using alpha equals 0.01 that the mean driving distance of Par Inc. golf balls is greater than the mean driving distance of Wrap Limited golf balls? Okay, so that's what we're looking at here. Now I'll move back in a second just to sort of confirm all the values we're using, but just a sort of quick remark in case you're not familiar with this term, that term there, alpha equals 0.01, that is the significance level we are using. Again, that just in case you're just joining us, that's the alpha value. So let's move on. Now, so the first step is to develop a hypothesis of what we're interested in. Now, again, up at the top here, we're interested in the difference of two population means. I'm just going to write that population means. Mu1 minus mu2. Now, there's several different ways we write out a hypothesis test. I won't really have time to go over it in this procedure, but what we were interested in the first instance, I'm going to write it down here at the bottom. Mu1 equal to mu2, and that is to say no difference. Okay, if mu1 is greater than mu2, there is a difference. Now, just a sort of quick way of re-expressing this second expression here, there is a difference, and we can write that, and my spelling's gone, there we go. We can write this expression here, mu1 greater than or equal to mu2, this is directly equivalent to this expression here. Okay. Or likewise, it could have less than rather than greater than sign. So this is the alternative hypothesis here, and it's greater than or equal to greater than 0. Now the null hypothesis is the opposite statement to the the alternative hypothesis. So if this is greater than 0, the null hypothesis expresses less than or equal to 0. Okay, so in this case, it does not exceed 0, is how we might express that. Okay. Now, the mu1 is the mean distances for population for Par, and mu2 is the mean distance for population of Wrap golf balls. Okay. Now we specify the significance level. Okay, no, 0.01. That's I pointed that out already, so that's another job done. So. Writing out the alternative, null and alternative hypotheses is an important step. So you will be expected to have something very. In most undergraduate statistics modules, you'll be expected to have something like that written. Okay. Now, so what we're going to do is compute the alarm signal. What we're going to do here is actually compute the test statistic. Okay, and this is what's also known as the test statistic. Okay. Now, the general structure is point estimate minus the expected value under the null hypothesis. I'm just going to call that null value, which is to sort of say, under the null hypothesis, what value are you expecting roughly? And this is all over the standard error. Okay, so let's just see. This is a point estimate, is this part here. This is the point estimate here. This here is the null value, and this part here, which I'm going to paint a circle in magenta, this part here is the standard error. Now that's the most important part of this. The point estimate is something we would calculate from a different calculate from a different the two different means. So actually there's a typo there. That should be 275. I'll just write it out again. The point estimate is 275 was x1 and x bar 2 was 258. So we see a difference for the samples of 17. Okay. Now the null value is 0. On the null hypothesis, we don't expect any differences. Okay. So in the last case where I've written it previously, we had a 0 there. Okay, so it's essentially whatever value goes in there. Now, the standard error is the tricky part. Now, it's the same standard error as you would use when you are computing a confidence interval. That isn't the same for each type of test, but here that is, it's sigma 1 squared plus sigma 2 squared over n1 plus n2. Just a reminder, sigma 1 was 15. That's the standard deviation for population 1. Sigma 2 was 20. The sample sizes were 120 for group 1, and group 2 was 80. Okay. So anyway, we have 17 minus 0 all over the standard error. The standard error, as you can see, works out to be 2.62. 17 minus 0 is 17. So our test statistic works out to be 6.49. Okay, that's a big step there. That's the major part of the calculation. Okay, so determine the critical value and then the rejection rule. So this is, you would go to your statistical tables. And you would pick out a value from the statistical tables. Now, with regards to the statistical tables, it is too much to do in a presentation like this. You should have it like sort of done already. Essentially, what you should do is you should come out with a critical value of 2.33. Okay. Now, if you're not quite sure about that, I'll do a different presentation specifically looking at how to compute critical values. Again, just as a remark, something I should have probably touched on earlier, or reminded ourselves on earlier, is this test here. This is a one-tailed test. How do you know? Because it has that greater than sign there. So it's a one-tailed test. We have the significance level alpha, and we also know that the population values are known. So a one-tailed test. Now determine whether to reject 0. So the test statistic, reject null if the alarm signal, or otherwise the test statistic is greater than 2.33. Because the test statistic is equal to 6.49, which is greater than 2.33, we reject the null hypothesis. The sample evidence indicates that the driving distance of Power Inc. golf balls is greater than the mean of the WRAP golf balls. Okay, that's enough on that.